guys for turning up for the last lecture. I hope you've enjoyed the series. I really have enjoyed chatting with all of you and getting to know you more.
We have to.
So today we're going to talk about kind of summarizing what's been going on during the whole series, but then also looking to the future and seeing really how can we pin down or find out what this dark energy is, this mysterious component that apparently is, you know, the majority of the universe. So that's why I called this lecture The Footprints of Dark Energy. Okay, so right now, all of you can answer these fundamental questions. So, because there will be a test at the end. So, no, I'm joking. So, okay, so after 8 weeks, pretty much this was the plan for the lecture series, that we were going to cover each of these questions in detail and give you some understanding of these are the questions that drive physicists, right, that make us turn up to the office every day, or maybe not, just make us work from our bed. But these are the questions that we're going after. So, you know, we spoke about in the early lectures, what is the universe made of? And I'm going to talk about that pie chart again. What has been its evolutionary history? So, you know, how did it begin? How did it evolve? How did we get to the state that we're in now? And then looking in detail, like how did the objects, the beautiful things that we see around us, like stars and galaxies and clusters of galaxies, how did these actually form? And then looking in detail at two of the major components of our universe, dark energy and dark matter, well, you know, what are the properties of these? And then, you know, very, very interesting questions of what are the evidence? What are the evidence for these two components, and can we trust that? So, in case you've forgotten, or in case so we'll just do a small recap over the answers to these questions. Okay, so what is the universe made of? So if we were to look at a pie chart of just the matter in the universe, then it would look like this. The familiar stuff, when we look out into the night sky, are the stars, which make up about 3%. The rest of the kind of dust and gas that hasn't made it to the level of stardom is really the 17%. So that just kind of represents the ordinary people like you and me in the world. But then when we look out further, we see that 80% of the matter in the universe is this dark component which does not interact with light. And we call that the dark matter. So the familiar things from the standard model of particle physics, which are the quarks and the leptons, all of these fundamental particles really just go into this wedge here. And considering the detail, the number of particles, all their different interactions, their symmetries, all the interesting and beautiful things that make up the standard model of particle physics just fits in here, it is a bit naive of us to think that maybe there's just one dark matter particle. That would be a little bit odd, but at the moment this is the assumption we're working from, the simplest assumption. But maybe there is much richer physics in this 80% wedge that we have yet to find. Okay, so most of the mass in the universe is made of something else, not atoms, and we call that the dark matter. Then if we were to look at, well, what about the total energy in the universe? Okay, the total amount of stuff in the universe. Then this dark matter is not really, you know, the whole story. That's 25% of the stuff. The normal matter is 5%. And then the rest of it is this unknown component, the dark energy, which, you know, we spoke a lot about. And we consider this a really mysterious component, which is causing a late-time accelerated expansion. So this is also a dark component in the sense that it does not interact with light. And that's why we call it dark energy, or why Mike Turner nicknamed it dark energy. So those of you that don't like the name dark energy, the alternative that Mike was thinking about for this title was silly energy. So I think of the two, I would say dark. Okay, so where did our universe come from? What happened in its evolution? So just to remind you of this story of the expanding universe, that when Einstein was writing down his equations of general relativity, which told us of how matter and space-time interact, and how one dictates how the other one moves, and how matter dictates how space-time curves, that really at that time people thought that the universe was a static, unchanging place. This is a very beautiful notion for people to contemplate. But really, that didn't work in Einstein's equations, despite how much he tried. And then it took observational evidence, so astronomer like Edwin Hubble making measurements of Cepheids at different distances to tell us that really the further away galaxies are, the faster they are receding from us. So this notion of an expanding universe. Things are expanding away from us today. And then if you roll the clock backwards, then you get this notion of, well, if everything's moving further apart today, you roll the clock backwards, things get closer and closer together, and we're left with this notion of a very hot, dense state that the universe started in. And then we have what's our information from that very early time. Well, that comes from satellites like the Planck satellite. So this is a picture of the cosmic microwave background. The picture we have of the universe when it was about 380,000 years old. And this really is our, the very first information that we have about those early stages of the universe. So these hot and cold spots are representing fluctuations, so these harmonic oscillations. You can think about them as sound waves or music waves in the early universe, when the particle soup that existed then was sloshing about. And those oscillations, those waves got frozen in. So very much like waves on a lake, sometimes in the winter here you can see waves get actually frozen but on the lake here. So these are kind of waves that have gotten frozen in or imprinted in the photons, in the light coming to us from that early time. And these density fluctuations are very, very small. So overall, the light that is coming to us from that early time is very homogeneous and smooth. But there are very small fluctuations, and it's very important that they are there because those are the seeds for structure formation later on in the universe. These very small deviations from uniformity at a part in 10 to the minus 5. So very small deviations. But they're very important because these grow and they form the structures that we see today. So when we fast forward 13.7 billion years, we see a very different picture of the universe. Okay? So this is a composite image from many different surveys showing galaxies. Right? This is our galactic plane here in the middle. And as you can look out, you see these galaxies form structures, really interesting structures, which we spoke about last week, which make up this cosmic web. And people who run simulations or people who study the universe are trying to understand how do we get from this picture here of a very young baby universe to this old universe that we see today. How do you form these structures? Right? How do you form the pattern that these structures create when we look out into the night sky? So this really is at the heart of cosmology, right? Trying to get from those initial conditions, trying to get as much information out of that picture that the Planck satellite is giving us. Get as much information out of that, create a consistent model, evolve it forward in time, either using computer simulations, or if you're lucky, if you have the equation for everything, you could just write that down and see if it explains the universe that we see today. So when I showed you computer simulations, this is one of the ways we tackle this really, really big problem. Right? This is very computationally expensive to create a mock universe. What you're doing is you're creating smooth initial conditions. We have evidence from this, from the cosmic microwave background, that things were very homogeneous and smooth. So you use this as the initial conditions in your simulation, and then inputting the laws of gravity, you run the simulation forward in time and watch the creation of the cosmic web. So you see matter flowing along filaments into overdensities, these dense clumps, or dark matter halos. So this is really going after the question of how did objects form in the universe? How did we get galaxies? And one of the main components of our theory for how galaxies form is this dark matter web. Okay, so this is a cosmic scaffolding where galaxies are born. So galaxies are born in these overdense regions, which we call dark matter halos. And in this computer simulation, you can see that under gravity, you get these filaments being formed. Matter flows in along these filaments into an overdense region. You can see that there's many satellite particles here, basically moving in and falling in and out. And ultimately, in this overdense region here, this is the place where you get a galaxy forming. So you get gas and dust flowing in along the filaments into this gravitational potential, cooling down enough to form stars. And then because this is gravitationally bound, this is the place where we'll have a galaxy, or maybe many galaxies, depending on the actual mass of this dark matter halo. So then we also wanted to look at, well, what are the properties of these mysterious components? the dark matter and the dark energy. Excuse me. So we went in detail through all the observational evidence we have for this dark matter component and why we think about it as a matter rather than an energy component. And we spoke a lot about the historical evidence, the very first evidence that something was going wrong in our standard model, which was the motion of astronomical objects. So looking at these rotation curves of galaxies, and basically showing that stars at the edge of the galaxy were rotating so fast that if you only looked at the luminous matter that was there, there wasn't enough matter to gravitationally bind those stars. They were just moving too quickly. They would have been flung away from the galaxy. You needed more matter there in order to maintain those type of velocities. And we ended up getting observations which showed very flat rotation curves as we went out to higher and higher radii away from the center of the galaxy. And if there were no dark matter, this is the type of rotation curve which you would expect. So this was one of the first evidences for dark matter. I also spoke about bulk flows. So we have really beautiful measurements now of the flow of material in our local environment. And this is a picture of one of those, where we're able to map out the velocity field. So how fast things are moving in the space all around us. And obviously, the amount of dark matter, the gravitational interaction of that dark matter with galaxies will determine how fast these bulk flows are. This net flow of material in the universe. And based on these measurements, we can actually then deduce how much dark matter is there. We also looked at the mass, how the mass affects the light from distant galaxies, so this notion of gravitational lensing. So that light from distant galaxies gets bent when it's passing by a very massive object. And even if we don't see what the massive object is, so if it's a large lump of dark matter sitting there, we can still measure the deflection of the light and how much the light is being deflected, and from that we can infer the amount of mass that is sitting there. And this is one of the key ways that we map out the dark matter distribution in our universe. We can also look at the measurements of the clustering of galaxies, so in a sense counting the number of objects of a certain size. Okay? And if you remember that picture of galaxy formation that I spoke about, you need a dark matter potential well in order to form a galaxy. And you need even bigger gravitational potential wells to form clusters of galaxies. So when we go out and we count these clusters of galaxies, they're telling us something about the size and distribution of the gravitational potential wells which the dark matter are causing and sitting in. So we also have the very important story of galaxy formation. If you want to form galaxies at all, you need dark matter. We can't get away from that. And then we also have information from the cosmic microwave background telling us that there is a dark matter component, and those distribution of hot and cold spots really tell us how much dark matter we need. And there's also the poster child for the existence of dark matter, which is this bullet cluster, which is a collision of two galaxy clusters, where we can map out where the dark matter is meant to be using this gravitational lensing technique. So the dark matter is shown in blue here at the side, whereas the hot gas, which was in the two clusters, has stalled here in the middle. So it's really showing a discrepancy between the luminous component and this dark component that make up the mass of a cluster. So we also went over what was dark energy, or what are the properties of dark energy. We still don't know what dark energy is. So the evidence for dark energy, we had some pointers before 1998, before these two teams of astronomers made these measurements of type 1a supernova. We had some hints from the cosmic age problem. So basically, after doing all the math and adding up what the age of the universe should be, if there was only matter in it, we got a figure of about maybe 12 billion years old. But when we actually looked at the age of the oldest star clusters, we got something closer to 13.7 or 14 billion years old. So there was that real problem for the theory before the measurements of the type 1a supernova. So the supernova observations really nails down this fact that the universe was not just expanding, but that expansion was accelerating. So these supernova allowed us, they were standard candles that allowed us to measure distances back in time out into the universe. We also had evidence from the growth of clusters. So the CMB was telling us that the total cosmic inventory, if we add up all the stuff in the universe, we should get something which equals 1, okay, in some units. But what we were finding from the growth of clusters and the large-scale structure, just counting all the stuff that we see and don't see, including the dark matter, we were getting a value of 0.3. So, doing very simple math, we were able to figure out there's a 0.7 here missing. And that must be the dark energy. Okay, so the properties of dark energy, we did speak a little bit about this. So the properties of dark energy come about from our observations. The observational evidence are telling us what these properties have to be. Okay, so we're letting observations guide our theory. We're not just writing down what we want the dark energy to be. So the best way to compare, to look at the properties of dark energy, are to compare it with dark matter and to really reconcile ourselves to the fact that they're very different components. That dark matter clumps, okay, whereas dark energy is very smoothly distributed throughout the universe. And if this was not true, we would not have galaxies forming and not have the cosmic web which we see today. We also have that evidence that the dark matter is pressureless, with a rest mass that is dominating the matter energy density, that we really need this dark matter to form galaxies, and it has been very important since the evolution of the universe, since very early times. Whereas dark energy, if we think about it as causing an accelerated expansion, we can think about it as a repulsive gravitational force. So this is an unusual idea to think about, but because it has this peculiar property, it can really only have been important quite recently in the evolution of our universe. We cannot have had a negative gravitational force be dominant at early times, because then you never would have gotten galaxies forming, you wouldn't have gotten dark matter halos. So we really have to, whatever model we write down for the dark energy, we better make sure it's only important quite recently. And then depending on what your dark matter is doing, we know that it interacts through gravity, because an example is gravitational lensing, where we see the deflection of light. So, but depending on what the dark matter particle is, it may also have some other interactions, like the weak force, if it's a weakly interacting massive particle. Whereas, as far as we know, the dark energy interacts only via gravity. And one of the best candidates we have for the dark energy is this notion of a quantum vacuum, where you get these fluctuations of virtual particles. And we know this happens, okay? We know in quantum field theory that you get these non-zero energy associated with the vacuum. And the really nice thing is that this quantum vacuum has exactly the properties of dark energy that we observe. But if you remember, the value of the energy density associated with the quantum vacuum is much, much bigger. And when I say much, I mean 10 to the 120, bigger than the measured value of dark energy. So this discrepancy means that we're not just closing the book on dark energy. We still don't know what it is. Okay. So that's a recap of basically everything you guys know already. So you should have been bored. You can wake up now.
If we can change.
Okay, so looking to the future, we have this notion now of precision cosmology. So I guess in the early days of cosmology, people didn't quite take it seriously, because the whole notion of seeing outside our own solar system or outside our own galaxy was kind of laughable. People were like, oh, we'll never be able to do that. But now we're in an era where we have exquisite measurements, not only outside our own galaxy, but of other galaxies, very, very far away, and we're able to map out the structure of space-time right back to the very beginning, which is the cosmic microwave background radiation. We have that evidence coming to us from very, very early times. So really now we're in an era of precision cosmology, where we can put convincing error bars on these measurements of the components of the universe. What is dark energy, dark matter, and atoms? So these numbers are not, wishy-washy, and we have some nice, very nice results from lots of different observational probes which use different physics, and they all agree on this picture, right? We haven't found anything that disagrees with this picture. So this is, even though you might not like it, this is what we're looking at for the components of the universe. And this is what has led to our standard model, which we call lambda CDM. So the lambda is for the dark energy, and the CDM is the cold dark matter component. So if you're a cosmologist today, what you really want to be thinking about are, well, we need more information about this, right? If this is the big thing you're going after, and also dark matter. These are, huge components of the universe, and we don't know much about them. So we need to think, well, what are the footprints of these two things? And if we focus on dark energy, we can ask the question, well, what are the interesting probes? If I write down a theory of dark energy, what effect will it have on, say, the growth of structure, for example? And then how are surveys addressing these questions? So what surveys are coming up next? And if you're interested in following this, there's lots of links on the handout today of different surveys which are going after the question of what is dark energy. So the ways to test dark energy, you can think about it in two ways. So the first way to test dark energy is the way that it was discovered, right? Looking at the expansion rate, making more and more precise measurements of how our universe is expanding over time. So we had those supernova measurements from 1998 from the two teams that won the Nobel Prize, and they were using this idea of standard candles. So if you have an object of a known luminosity at different distances, then basically you can map out the distance to those objects using an inverse square law. And these supernova, the type 1a supernova in particular, do represent standard candles in the sense that they give off a luminosity, a fixed luminosity. So these are very, very massive detonations. This is a picture of one. This is a galaxy here, and this is the supernova detonation, showing that these are such large explosions of a star at the end of its lifetime, or a binary star system, that the light from the supernova actually outshines the light from the galaxy itself. And we regularly see these, and we see them at different distances from us. So we're able to map out the expansion history in this way using this standard candles approach. There's another interesting idea, which is, well, if you had a standard ruler, if you knew something was a fixed size in the universe, then if it was at different distances from you, based on how the size of that object appeared to change, you could then map out what the universe was doing in between, how the expansion was changing the size of this fixed ruler. So this is the idea of a standard ruler in cosmology. And we do have a standard ruler, so nature has been very kind to us. So this standard ruler that we have comes from the cosmic microwave background. So if we go back and we think of that particle soup, that quark soup in the very early universe, which was sloshing around, that you had these musical notes or musical oscillations in. And then at the time that the photons were released from that soup, okay, the time of recombination, what we get is the frozen wave. And when we look at the cosmic microwave background, we're seeing the radiation that is frozen at that time. But it also turns out that these acoustic waves that are frozen also get imprinted in the matter component. So when we see hot and cold spots of a certain size in the radiation from the very early universe, the size of those hot and cold spots are also imprinted in the distribution of matter. And as you can imagine, when we look at the matter, the photons have been traveling to us from very early times, relatively unaffected until today. But as we said, the matter has been undergoing a lot of change, right? This clumping into galaxies and galaxies into clusters. So this cosmic ruler is actually a much weaker signal in the matter distribution compared to the radiation distribution. So you can think about, so when I say a cosmic ruler in the matter distribution, what I mean is there's a preference for galaxies to form at a certain distance from one another. And this is due to these peaks or over and under densities in the primordial plasma. That's a lot, isn't it? Okay. So we have a nice name for these. These are called Baryon Acoustic Oscillations, or BAO. But they're definitely not to be confused with these tasty dumplings. But you can keep that in mind if you're waiting for lunch at 12 o'clock. Okay, so in detail, what are these Baryon Acoustic Oscillations? So you guys have heard about the cosmic microwave background radiation, where these hot and cold spots are in the photons, right? We're seeing these frozen waves in the radiation. And then we can plot out the temperature difference as a function of scale, and we see the size of these hot and cold spots. This is basically what this curve is telling you, just the size of the hot and cold spots as we go along, and the relative importance of them, or the abundance of them. But we could also make a plot like this for the matter distribution. So the matter distribution also has these waves imprinted on it. But then we also have to factor in the fact that since the time that the CMB was released until today, the matter has undergone a lot of change, okay? A lot of gravitational interaction and clumping. So this signal has understandably been washed out. So earlier in the lecture series, I showed you this plot of the temperature difference with all the data points overplotted from Planck. And I told you that those measurements and the data line, the theory line was not a fit to the data, that those measured points fell on our theory curve. And we had an extremely exquisite measurement of the temperature differences in the radiation component. But when we tried to measure the sound, this cosmic ruler in the matter distribution, that our measurements are not as precise in terms of our error bars are much, much bigger. So this is showing you a plot of the measurement of this Baryon acoustic oscillation, so this bump in the matter distribution from the SDSS sky survey. And you can see the error bars are a lot bigger. So the black points are the measured. This bump here, you can think about this as kind of corresponding to the first peak here in the radiation component. So what this is telling us, this curve here is just looking at counting pairs of galaxies and the distances from one another. Okay, so you're just saying, how many galaxies at a fixed distance from one another do we have? And it's showing that there's a preference for galaxies to be at a distance of 100 megaparsecs from one another. So if galaxies were just randomly distributed in the universe, we would actually get 0 for this correlation function because of the way we've normalized it. But we would not get this interesting feature, right, of this bump, but also we wouldn't get this amplitude here. So there's lots and lots of physics in this correlation function. Basically, this is telling you that there's a remnant or echo of these oscillations being left over in the matter distribution, which means when galaxies form, there's a preference for them to be at a fixed distance of 100 megaparsecs. Okay, so that's just statistically, it doesn't mean they're all at 100 megaparsecs from one another. It just means that there's this little imprint, okay, they still have a faint memory of the oscillations in the early universe. And that's really interesting. Because if we remember back to those simulations of cosmic evolution, so much has gone on, which has maybe washed out this signal. So making this measurement is quite difficult, as you imagine, but we have done it. And now this is what I mean by precision cosmology, in that this position of this first peak, this preference for galaxies to be at a distance from one another of 100 megaparsecs, is telling us things about the matter component. So here overplotted are some theory lines for different densities of the matter component in some weird units. So you don't need to worry about that. But if there were no BAO, okay, if there were no echo of those oscillations from the early universe, we would get this purple line here. Okay. So the data are definitely showing us this memory of the early universe in the clustering of galaxies. Okay. So the second way that we can test dark energy is by looking at the growth of structure. So we spoke about the evolution of the universe and the accelerated expansion, and mapping the expansion history tells us about dark energy. But then we can also look at the growth of structure. So we think dark energy is a negative pressure component. So you can think about it as a repulsive force on large scales. So obviously this is going to affect the growth of structure over time. Okay? If you try to form galaxies at an early time, you can ask questions like how much does dark energy affect the growth of galaxies at early times? And by looking back in time, by looking at galaxies further and further away from us, we can actually map out their growth over time. And look at, well, how sensitive were they to dark energy? So one telescope that's doing this is the South Pole Telescope. This is a picture of it here. So there's many people at the University of Chicago that work at this telescope. And they come back telling me wonderful stories of what it's like to work at the South Pole Telescope. So it's a very interesting place, although I don't think I'd like to go because you're only allowed to shower like once every 3 days or something. But I mean, it sounds fantastic. So they have this beautiful telescope. And one of the things they're doing is that they're looking at this cosmic microwave background radiation. But the interesting thing is that these massive clusters, right, these clusters of galaxies, they're actually blocking out some of the cosmic microwave background radiation. So they are creating a shadow in the CMB, which the South Pole Telescope can measure. So this is showing one of those shadows from a cluster, a massive cluster of galaxies. This is the optical image of the cluster, where you can see all the individual galaxies. But this is what it looks like to SPT. SPT is trying to see the CMB, and these clusters are getting in the way. So the technique that they use is called the Sunyaev-Zeldovich effect. So it's basically in the cartoon here, it's showing the microwave background photon coming into the cluster. There's hot gas in this cluster, and by inverse Compton scattering, you're getting the CMB photon scattering off hot electrons, and that hot electron is actually changing the energy of the CMB photon. And what that means is then you end up with a CMB photon, which basically has been increased in energy, and then we see this shadow here. So this is the cluster in the optical, and then this is what the cluster looks like to the South Pole Telescope, so this shadow here in the CMB. So in this way, we're able to map out the mass of the cluster, and we're also able to do this as a function of redshift, so looking back in time. And this is one of the ways we can test the growth rate and the effect of dark energy on the growth of the structure. So where are we at the moment? So I think it was in 2005, the National Science Foundation, NASA, and the Department of Energy created what's called a Dark Energy Task Force, which sounds like a really cool thing to be on. And they came up with these 3 points. They came up with lots of suggestions, but these three key points which we're going after in the future. So this is the thing that theorists and observers are trying to answer. So the first thing is determine if the accelerated expansion is due to a cosmological constant. So those of you that were in the earlier lectures will remember we spoke about a cosmological constant as having an equation of state or some kind of elasticity associated with it, which is the ratio of the pressure to the energy density, which should be -1. Okay. So you can think about it in the future, observers are trying to find out, is W equal to -1? So a lot of people joke and say that cosmology has just been reduced down to this one question. We're trying to measure one number. And at the moment, we have that W is very, very close to -1. But there are error bars on that number, and we want to shrink those error bars down. So if W is not equal to -1, then we're looking at some interesting physics. Okay? Then it's not a cosmological constant. And if the acceleration is not due to a cosmological constant, and there are some dynamics in terms of this dark energy might be a scalar field, for example, that's changing over time. So it may be something very, very new in the universe which has some interesting dynamics. Maybe it did something crazy a billion years ago and changed. Or maybe it was just very, very boring. But we really want to answer this question, what is the evolution of this equation of state? So this is focusing on the properties, the ratio of the pressure to the energy density of dark energy. And then we also need to think about, well, what if it's not a scalar field, or what if it's not a cosmological constant or a dark energy component, but what if we really need to modify our theory of gravity on large scales? So maybe general relativity, although it works incredibly well in describing the solar system and how astronomical bodies move in our solar system, it works incredibly well in explaining binary pulsars. So I spoke a lot about the beautiful tests, the beautiful measurements that have been made which confirm GR to exquisite precision. But what if on very, very large scales, or maybe in underdense regions, the theory of gravity needs to be modified a little bit? So the way we can do this are those 2 previous tests I spoke about. So this combination of mapping out the expansion history over time using cosmic rulers, standard rulers and standard candles, and then also comparing this with the growth rate of structure, comparing this with how those clusters build up over time. So in this way, we have a consistency check of what the properties of dark energy are and what they're doing. Okay. So one of the main surveys that is actually going on now and started last year is this dark energy survey. So this is a picture of the telescope here. This is where it's situated in Chile, on the Sierra Chololo Mount. This is a 4-meter telescope which started taking data last year. And many people in the University of Chicago and Fermilab are involved in this project. And the camera is really producing some exquisite pictures. So very shortly after turning on, this was one of the very first pictures that this took. This is a picture of a galaxy in the Fornax cluster, and this is incredibly beautiful. And it's really showing the precision optics that we have nowadays. So this is the state of the art. And what the Dark Energy Survey is going to do is hopefully answer those questions about the expansion history, so the evolution in that W parameter, and also looking at clusters over time. So it will run for 5 years, started last year. They've already had some amazing results out in published papers on the archive. So eventually they're going to map out 300 million galaxies, an eighth of the sky, and go 2.5 magnitudes deeper than the Sloan Digital Sky Survey. And as I said, it started last year. So we really look forward to the results from this survey and what it can tell us about the properties of dark energy. We also have the LSST, which is the Large Synoptic Survey Telescope, which is a ground-based telescope, which will be also situated in Chile. Is due to start in 2018. And this is going to push those numbers even higher. So looking at 10 billion galaxies now, imaging half of the sky every 3 nights, 5 magnitudes deeper than SDSS. And one of the real challenges with LSST is the amount of data that it's going to generate. Okay? So we're not going to physically be able to look at all this data in a single postdoc or postgrad's lifetime, right? 30 terabytes of data per night. And then over 100 petabytes over 10 years. So a terabyte is 10 to the 12 bytes. This is an awful lot of data. Storing it is one problem. Analyzing it is another. So one of the things I'm a bit afraid of is that future cosmologists might end up just being data scientists. But according to Forbes magazine, that is one of the sexiest jobs of the century, so maybe we shouldn't worry about this. So the LSST is certainly going to present a challenge, not just in answering fundamental questions, but also just in how do we deal with the amount of data that we've taken. And then looking even further into the future, what is planned in terms of satellites, space satellites coming up. I think planned for about 2020 will be the Euclid space satellite. This is a European Space Agency satellite which has been approved, and people are planning for it now. And then on the American front, we have the NASA mission, which is planned, called WFIRST, the Wide Field Infrared Survey Telescope. So I think at the moment, WFIRST or NASA were donated 2 better than Hubble telescopes from the US military, so these are going to be used for this mission, I think. So that begs the question, what are the military using if they don't need these Hubble telescopes? Okay, so one of the other interesting things, just to bring you up to speed, Austin Joyce spoke a lot. If we go back to the beginning of this lecture series, he spoke a lot about BICEP2's exciting recent discovery of gravitational waves from the early universe. So this is really, really cutting edge research in terms of people are still arguing right now about the implications for this, and we have lots of other experiments which are trying to confirm it. And at the moment, one of the big doubts is this measurement of gravitational waves from the early universe in the polarization of the light, which will tell us a lot about inflation in the early universe. Could this be due to dust? Okay. So one of the headlines, I don't have it up here, was BICEP2 has basically had dust on its glasses when it was making this measurement. So at the moment, we really don't know. And what people are waiting for are for the Planck team, the Planck satellite, to really talk about this, and they haven't so far. So the Planck satellite is up there making similar measurements they're making measurements over the whole sky instead of BICEP, which is just staring at a small part of the sky. The Planck satellite also sees dust, but this is the dust map which they released a couple of weeks ago, and unfortunately this is the region that BICEP stares at. So they cut out of their map the region that BICEP looks at, because they're not yet ready to release this data. And they've said that they will do that by October this year. So in terms of this really exciting fundamental physics discovery of gravitational waves from the early universe, we're still out on that, okay? So we still don't know, and we should know by the end of this year. But if it confirmed, this is really exciting. And this would open up new areas of physics in the same sense that when we discovered the cosmic microwave background, it opened up so many new areas of physics. Okay, so that's really everything I have to say for now, but I'm going to show you a movie for the last 5 minutes. So hopefully this will work. So let me tell you a little bit about this movie. This movie was created in Durham University in the UK when I was a grad student there, and I helped out making it. And this is an award-winning movie called Cosmic Origins. It's actually meant to be a 3D movie, but I don't have the setup for that today, so you're just going to have to watch it in 2D. The images from the first start of the movie are all real images from the Hubble Space Telescope. And then the second part of the movie, the images are from computer simulations. So I kind of like this movie because it sums up everything I wanted to get across during this lecture series in terms of what we're doing, what we're trying to understand, and how far we've come in understanding our cosmic origins. So that's what the movie's about.
Can you reduce the light?
Yeah.
There is no bigger quest in science than the search for our cosmic origins. How was the world created? What is special about it? What does the future hold? Let us begin the search by looking out into the cosmos around us. The Moon and the Earth are held together by gravity. At a distance of 400,000 kilometers, the Moon is the furthest man has traveled. Apollo 11 took 4 days to get there, but a beam of light can complete the journey in a little over a second. 8 light minutes away lies the Sun. Its gravity dominates the solar system, causing the planets to orbit around it. The Sun formed 4.5 billion years ago from a cloud of gas and dust. The leftover debris collected over time to form the Earth, the Moon, the rest of the solar system, and us. The Sun is part of the Milky Way galaxy. In it, new stars like the Sun are forming in special places like the Orion Nebula, 1,000 light years away. The nebula is a vast complex of gas and dust, 2,000 times the mass of the Sun. Stars form as clumps collapse due to the pull of gravity. The collapse is halted when nuclear reactions ignite in the core. Orion is lit up by the light from newborn stars. Some host embryonic worlds, perhaps resembling the Earth. Let us now head to the heart of the Milky Way, 20,000 light years away. These stars are moving at thousands of kilometers per second. But why are they moving like this? The gravity of an invisible black hole, 4 million times more massive than our Sun, holds them in orbit, just like the Sun holds the solar system together. Imagine if we could remove the gravity of the black hole. The stars would fly away. The Milky Way is a spiral galaxy, a vast disk of stars and gas with a central bulge. It contains 100 billion stars and is 100,000 light years across. But the stars are moving too fast to be held together by their own gravity. There must be more than meets the eye. Astronomers deduce that the galaxy is embedded in a clump of invisible dark matter whose gravity binds it together. Telescopes, like the Hubble, have surveyed our universe, revealing that the Milky Way is just one of many billions of galaxies. Flying further from the Milky Way is like traveling back in time. We see galaxies whose light has taken billions of years to reach us. The galaxies change in appearance and color. We see young blue galaxies with odd shapes, which are forming hundreds of stars each year. As we get near to the beginning of the universe, there are fewer and fewer galaxies until eventually there is only darkness. About 500 million years after the Big Bang, galaxies had not yet formed. How are galaxies made? A tiny fraction of a second after the Big Bang, quantum processes seeded the universe with small irregularities. Their evolution from the Big Bang to today can be traced in a supercomputer. Over billions of years, gravity pulls lumps of dark matter together, building ever larger structures inside which galaxies can grow. Physicists have yet to identify the dark matter. It is probably an exotic elementary particle which must be very different from the ordinary matter which makes up the sun, the earth, and all life forms. To understand how galaxies form, the computer must be taught how to solve the equations of physics that control the behavior of matter. With its overwhelming gravity, dark matter, shown on the right, sets the galactic agenda. Ordinary matter, on the left, cools inside clumps of dark matter and turns into stars. As the stars age, they eventually run out of nuclear fuel and stop shining. Massive stars explode spectacularly as supernovae, scattering newly fused chemical elements that find their way into new generations of stars, planets, and eventually living things. What will be the fate of the Milky Way? Our nearest large neighbor, Andromeda, lies 2.5 million light years away and is hurtling towards us at a speed of a few hundred kilometers per second. In a few billion years, the two will become entwined in a cosmic dance. Gravity, the architect of our universe, will rip stars and dark matters out of each galaxy. As the Milky Way and Andromeda fuse, a new galaxy will emerge. Cosmic evolution will continue to forge ahead. We have come a long way in our understanding of the cosmos, but future generations of scientists still have far to go in the quest for our cosmic origins.
Okay, I'll end there. Thanks very much. Any questions? Yes.
Near the beginning, you said that the standard model applies to the 17% that's gas. But does that also apply to stars?
Yes, yes, it would, yeah. That's right. Any other questions? Yes.
You use a graphic that has a big bang at one end and kind of fans out with the
Yeah.
satellites beyond. Do we know where we are in this universe?
So, so we know what the edge of the visible universe is. That's all the light that's coming to us. But in terms of where we are, I mean, do you mean relative to other galaxies?
Is there like
Yes.
a spatial map of this whole thing?
So, no, I mean, because the light coming to us is basically a sphere all around us, right? So we see that as edge of the visible universe is just a sphere all around us.
Yeah.
So in terms of our location, yeah, it looks like we're at the center of the universe, but it would look like that if you were at any other galaxy as well. Do you know what I mean? So, yeah.
We could reach the
Yes.
movie and the internet.
Couple of questions. First, you mentioned expansion of the universe and also acceleration.
Yeah.
Since we're dealing in a visual universe, is that, you mean physical acceleration like in a car? And if so, could you compare it to like my wimpy Corolla? Or space shuttle.
Oh, you have to give me some time to do those calculations.
So, I mean, is it a major...
It's not fast if you're worried about that. And also, I mean, so yes, you could compare it in terms of the units, but you'd get into kind of nonsensical, very big numbers that I don't want to hurt myself, so I don't want to do those calculations.
Oh, so it's a huge number, like more than the space shuttle.
So, no, the acceleration is very slow. And also, we don't have to worry about it in terms of we're inside a galaxy, gravitationally bound system, and, you know, relative to other things that we're interacting with, we really don't have to worry about the accelerated expansion. Yeah, but yes, it is an acceleration in terms of the velocity is a rate of change of your distance.
Sure.
The acceleration is the rate of change of that velocity, so it's exactly the same, the way we think about it.
My other question is this biceps data. You know, they talk about the graviton, of course, which is undetectable. And but I read that the gravity waves could shed some light on the graviton as being a particle. Is that something that could possibly be released by this bicep data, but perhaps people don't really believe in it?
So basically the bicep team, so yeah, I mean, if this is confirmed, if the signal of the gravitational waves is confirmed, then it's gonna be amazing in terms of our theory, right, for those gravitational waves in the early universe. And the signal at the moment was a lot bigger than people thought it would be, right? So at the moment, theory is still kind of catching up with if this is confirmed, if the gravitational wave signal is as large as it is, then the implications of that in terms of our theory, you know, you need to give us time to catch up with that, okay? This is real cutting edge science, and I think at the moment we're still at the level of trying to confirm the observation. But yeah, it's gonna be cool if it is confirmed. Yes?
May I ask a very silly question?
Of course, I love this.
Would the expansion of the universe be caused by something that's other than natural?
Something other than natural.
God.
So,
I mean, we thought that maybe if there's life somewhere else, intelligent life somewhere else,
yeah.
could they have been doing physics back then that could be causing what we're experiencing?
You're trying to blame the aliens.
I know there's probably...
No, I mean, so when you think about dark energy, really all bets are off, because when we understand some of the properties of it, but when you're a theorist sitting down trying to write, you know, what is causing this, being as creative as possible is good, but I've never seen any theories that try to blame it on the aliens. Yes?
How does gravity affect polarization?
So the gravitational waves, basically, they're imprinted in the radiation. The details of that I'm not going to go into. That is very, very technical, and I'd go back to Austin's lecture, or I would refer you to the expert over in the corner, well, Emil, for the luncheon afterwards. It's not my area of research, but I know Austin did go into this, how
he didn't
polarization
explain.
is changed. Sorry?
He didn't explain the mechanism.
So the mechanism is detailed, and I think that could be an entire Compton lecture series in itself, rather than me just giving you a 5-minute question, but yeah. Yes?
I'm left with a desire to see that movie in 3D.
Yeah, it's fantastic. It's absolutely
I wonder if that
fantastic.
could be arranged somehow. Maybe in Currar Library as a space.
So if you want to see it in 3D, you go to the Adler Planetarium,
Okay.
and down in the basement of the Adler, I'm not recommending, like, you know, this is a legitimate, it's called the Science Visualization Lab, which is in the bottom of the Adler Planetarium. They have it on a 3D screen there, and if you ask them, or if you go one of the days that I'm there, so KICP Saturdays, where we go for 2 hours and we talk to the public. If you want to see it, I would be happy to show you it there in 3D, and it really is spectacular. One of the things that really stands out is that when we're flying through the Orion Nebula, it's really, really spectacular. And one of the things I love is watching the kids try to catch the stars. And turn
I'm I'm also left with a desire to see the computer down in Oregon.
Mira, yeah, I don't think you'll get interested. Yeah, maybe try for a supercomputer that isn't in a national lab. Might be easier. Yes? Yes, you?
I think this term was mentioned last week, and they didn't have a chance to ask, but off the mesh shell, what is, I think it relates to the virtual particles, what does that really mean?
Yeah, it does exactly, yeah. So this notion of being on shell and off shell, this is, these are terms in quantum field theory for particles that obey equations of motion. So in a sense, familiar equations of motion that we can write down for how a particle should behave, that is the on-shellness, if you like. And then these crazy virtual particles we talk about as being off-shell, in that they do crazy stuff.
Have those actually in a laboratory setting been detected? Or
Yes, yeah, they have, yeah. Yes?
So Hubble postulated expansion based on redshift, and we've learned that the acceleration is postulated on brightness differences in standard candles. So since that initial discovery, has there been any empirical observation or studies that at those distances, those farther distances than Hubble was able to reach, that coordinate the redshift with the standard candle brightness variation?
Yeah, so you mean other mechanisms apart from the standard candle? Is that what you mean?
Yeah, in other words, think of it as confirmatory other means of
Which
observation.
involve other physics.
Yeah.
Yeah, so the standard ruler, that measurement of the BAO, that confirms an amount of dark energy, which we infer from the supernova results. It involves different physics, this notion of a standard ruler. It also involves physics at the CMB. So these are very different to the physics which go into looking at supernova luminosities and how those luminosities change with distance from us.
What about redshift?
So the redshift is involved, but to get very technical, you can remove your dependence on that redshift to the objects, to the cosmic ruler in a very fancy way, which I'm not going to talk about, but you can remove that. So in a sense, these measurements of the cosmic rulers, they do rely on different physics and physics from the CMB, which all give us that coherent picture of dark energy. Yeah. Any questions back?
In the slide, you showed the acoustic pressure wave function, plotting the correlation function versus the co-moving function. Between 100 megaparsecs and 200 megaparsecs, the error bars are enormous. Is that an artifact of the mathematics or the cosmological mind?
No, so this is old data.
Yeah.
But yeah, as you go to, so that's a really good question. As you go to larger scales, what's called cosmic variance, which are causing these error bars to blow up. So the size of those error bars will depend on the size of the survey, the size of the actual galaxy survey that you carry out. It'll depend on the galaxies you choose, the number of galaxies that you choose. So you're using these galaxies to measure distances, and if you only use a few galaxies, then your error bars get bigger, right? But then if your survey is only of a certain size, then when you make measurements on the very largest size, right, you only have very few measurements on those really big scales. So this is why you have to factor that into the error bars as well. So that's a really good question. This is why we need the bigger surveys, because then they're going to give us a bigger volume, they're going to give us more galaxies, and they're going to get us much smaller error bars in areas of interest on larger scales. It's a good question. Yes?
Why doesn't dark energy overrule the gravitational pull of black holes and dark matter and prevented galaxy formation and just let the universe to complete disintegration?
Yeah, so if you were, I think it was a couple of weeks ago, I showed this plot of the relative energy densities of different components in the universe and how they dilute with the expansion history. So basically the amount of dark matter and matter in the universe dilutes at a different rate to the dark energy, so that the dark energy naturally becomes to dominate today. So I think will we end there?
Yeah, I think so. Let's thank Elise for a wonderful lecture series.